primary purpose of a circuit breaker is to protect the circuit and its components from overcurrent, that is, excessive current flow. A circuit breaker is designed to trip, meaning to open the circuit, when the current passing through it exceeds a predetermined value known as the trip current. Wires have a maximum current carrying capacity, which is determined by their size and material. Using a wire with a current capacity lower than the breaker's trip current is a safety hazard, as it can overheat and cause a fire. In the given situation, a 4mm2, which is equivalent to 12 American wire gauge, wire has a current carrying capacity of 20 amps, while the circuit breaker is rated for 30 amps. This means that the wire is adequately protected, and the circuit breaker will trip before the wire reaches its maximum current capacity. However, it is not ideal to have a breaker rated much higher than the current capacity of the wire. This reduces the level of protection for the wire. There are several possible reasons why the breaker might be oversized. Firstly, it is possible that the load current may occasionally exceed 20 amps for short periods of time, and the oversized breaker provides a margin of safety in these situations. Secondly, the designer may have anticipated that the load may increase in the future, requiring a higher current capacity. Thirdly, circuit breakers come in standard sizes, and the 30 amps breaker may be the closest available option that provides adequate protection for the 20 amps wire. While the circuit is protected adequately with a 30 amps breaker, it is not considered best practice to have a breaker significantly oversized compared to the wire current capacity. For better protection and reliability, consider replacing the 30 amps breaker with a 20 amps or 25 amps breaker. To elaborate further on circuit breaker protection, it's essential to understand the different types of overcurrent conditions. These conditions primarily include overload and short circuit faults. An overload occurs when the current exceeds the normal operating current of the circuit but remains within the capabilities of the wiring. This can happen when too many devices are plugged into a single circuit, causing the current to rise gradually. Circuit breakers are designed to trip after a certain time delay under overload conditions to prevent nuisance tripping from temporary surges. In contrast, a short circuit is a more severe condition where the current takes an unintended path, bypassing the load and resulting in a rapid and dramatic increase in current flow. This is often caused by a fault in the wiring or equipment. Circuit breakers respond almost instantaneously to short circuit currents, tripping within milliseconds to minimize damage and prevent electrical fires. The National Electrical Code, or NEC, provides guidelines for selecting the appropriate circuit breaker size based on the wire size and the intended load. The NEC specifies the maximum allowable overcurrent protection for different conductor sizes, taking into account factors such as the conductor material, insulation type, and installation method. For example, NEC Table 310.15b16 lists the allowable ampacities of insulated conductors rated up to 2000 volts, based on an ambient temperature of 30 degrees Celsius, which is 86 degrees Fahrenheit. It is important to consult the latest edition of the NEC and any local amendments to ensure compliance with the applicable electrical codes and regulations. The ampacity of a conductor is the maximum current, in amps, that a conductor can carry continuously under specific conditions of use without exceeding its temperature rating. Several factors can affect the ampacity of a conductor, including the ambient temperature, the number of conductors in a raceway or cable, and the presence of thermal insulation. When conductors are installed in environments with high ambient temperatures, their ampacity is reduced because the heat generated by the current flow cannot dissipate as effectively. Similarly, when multiple conductors are bundled together in a raceway or cable, their ampacity is reduced due to the increased heat buildup. The NEC provides adjustment factors and correction factors to account for these effects and ensure that conductors are not overloaded. In this scenario, with the 12 American wire gauge wire and the 30 amps breaker, the primary concern is that the breaker may not trip quickly enough to protect the wire from overheating under overload conditions. While the breaker will eventually trip if the current exceeds 30 amps, the wire may be subjected to excessive heat for a prolonged period before the breaker trips. This can damage the insulation, leading to premature failure and increasing the risk of fire. To mitigate this risk, it is generally recommended to use a circuit breaker that is closely matched to the ampacity of the wire. In the case of the 12 American wire gauge wire with a 20 amps ampacity, a 20 amps breaker would provide the best protection. However, it is also important to consider the characteristics of the load being served by the circuit. If the load includes motors or other inductive devices that draw a high inrush current when starting, it may be necessary to use a slightly larger breaker to prevent nuisance tripping. In these cases, a 25 amps breaker may be an acceptable compromise, provided that the wire is properly protected and the installation complies with all applicable codes and standards. Another consideration is the voltage drop in the circuit. Voltage drop occurs when the voltage at the load is lower than the voltage at the source due to the resistance of the conductors. Excessive voltage drop can cause equipment to malfunction or operate inefficiently. The NEC recommends limiting the voltage drop in branch circuits to no more than 3%. The voltage drop can be calculated using Ohm's law, which states that voltage equals current times resistance. The resistance of a conductor depends on its length, cross-sectional area, and material. Longer conductors and smaller conductors have higher resistance, resulting in greater voltage drop. To minimize voltage drop, it is important to use conductors that are large enough for the intended load and to keep the circuit length as short as possible. In some cases, it may be necessary to use a larger conductor size than required for ampacity considerations alone to meet the voltage drop requirements. In addition to circuit breakers and fuses, other types of overcurrent protection devices are available, such as supplementary protectors and solid-state relays. Supplementary protectors are used to provide overcurrent protection for individual components or circuits within equipment. They are typically smaller and less expensive than circuit breakers and are not intended to be used as a substitute for branch circuit protection. Solid-state relays use electronic components to detect overcurrent conditions and trip the circuit. They offer faster response times and greater accuracy than traditional electromechanical circuit breakers, but they are also more expensive. The selection of the appropriate overcurrent protection device depends on the specific application and the requirements of the electrical system. Proper coordination of overcurrent protection devices is essential to ensure that the circuit breaker closest to the fault trips first, minimizing the impact on the rest of the electrical system. This is known as selective coordination and is required in certain critical applications, such as hospitals and emergency systems. Selective coordination can be achieved by using circuit breakers with different time current characteristics or by using fuses with different melting times. In conclusion, the relationship between circuit breaker size and wire size is a critical aspect of electrical safety. While it is possible for a 30 amps breaker to protect a 20 amps wire under certain circumstances, it is generally recommended to use a breaker that is closely matched to the ampacity of the wire. Factors such as load characteristics, voltage drop, and coordination requirements should also be considered when selecting overcurrent protection devices. Consulting the NEC and working with a qualified electrician are essential to ensure that electrical installations are safe and compliant with all applicable codes and standards. To expand on the topic further, let's discuss the different types of circuit breakers available and their specific applications. Circuit breakers can be broadly classified into two main categories: thermal magnetic breakers and electronic trip breakers. Thermal magnetic breakers are the most common type of circuit breaker used in residential and commercial applications. They use a combination of thermal and magnetic elements to detect overcurrent conditions and trip the circuit. The thermal element consists of a bimetallic strip that bends when heated by the current flowing through it. When the strip bends sufficiently, it trips the breaker. The magnetic element consists of a solenoid that is energized by the current flowing through it. When the current exceeds a certain threshold, the solenoid trips the breaker. Thermomagnetic breakers are relatively inexpensive and reliable, but their trip characteristics can be affected by ambient temperature and they may not be suitable for applications requiring precise overcurrent protection. Electronic trip breakers, also known as solid-state breakers, use electronic components to detect overcurrent conditions and trip the circuit. They offer greater accuracy and flexibility than thermal magnetic breakers and can be programmed with a variety of trip characteristics. Electronic trip breakers are commonly used in industrial and commercial applications where precise overcurrent protection is required. Within these categories, circuit breakers are further classified by their interrupting capacity, which is the maximum short-circuit current that the breaker can safely interrupt without being damaged. Circuit breakers with higher interrupting capacities are typically more expensive but are necessary for applications where the potential short-circuit current is high. The NEC requires that circuit breakers have an interrupting capacity sufficient to interrupt the available fault current at their point of installation. Circuit breakers are also classified by their voltage rating, which is the maximum voltage that the breaker is designed to operate at. Circuit breakers with higher voltage ratings are typically larger and more expensive than those with lower voltage ratings. The NEC requires that circuit breakers have a voltage rating equal to or greater than the nominal voltage of the circuit they are protecting. In addition to these basic classifications, circuit breakers are available with a variety of optional features such as ground fault protection, arc fault protection, and surge protection. Ground fault protection is designed to detect and interrupt ground faults, which are unintentional electrical connections between a live conductor and ground. Ground faults can be dangerous because they can cause electric shock and fires. Arc fault protection is designed to detect and interrupt arc faults, which are dangerous electrical arcs caused by damaged or deteriorated wiring. Arc faults can cause fires and are a leading cause of residential electrical fires. Surge protection is designed to protect electrical equipment from voltage surges, which are sudden increases in voltage that can damage sensitive electronic components. Voltage surges can be caused by lightning strikes, power grid switching, and other electrical disturbances. When selecting a circuit breaker, it is important to consider the specific requirements of the application, including the load characteristics, the available fault current, the voltage rating, and any optional features that may be required. Consulting the NEC and working with a qualified electrician are essential to ensure that the correct circuit breaker is selected and installed. Furthermore, proper maintenance of circuit breakers is crucial for ensuring their continued reliability and performance. Circuit breakers should be inspected regularly for signs of damage or wear, and they should be tested periodically to verify their trip characteristics. Circuit breakers that are found to be defective or damaged should be replaced immediately. It is also important to keep circuit breakers clean and free from dust and debris. Dust and debris can accumulate on the breaker contacts and prevent them from making good electrical connections. This can cause the breaker to overheat and fail. In addition to regular inspections and testing, circuit breakers should be lubricated periodically to ensure smooth operation. The lubricant should be a non-conductive type that is specifically designed for use with electrical equipment. The frequency of lubrication will depend on the operating environment and the manufacturer's recommendations. Finally, it is important to never tamper with or modify a circuit breaker. Circuit breakers are designed to protect electrical circuits from overcurrent conditions, and any modification can compromise their safety and effectiveness. If a circuit breaker is tripping frequently, it is important to investigate the cause of the problem and correct it rather than simply increasing the size of the breaker. Increasing the size of the breaker can overload the wiring and create a fire hazard. In summary, circuit breakers are essential components of electrical systems that provide overcurrent protection. They are available in a variety of types, sizes, and configurations to meet the needs of different applications. Proper selection, installation, and maintenance of circuit breakers are crucial for ensuring the safety and reliability of electrical systems. Consulting the NEC and working with a qualified electrician are essential for all electrical work.